Okay, yeah. I think I feel like I've talked enough this morning. So I'm gonna try to be brief, but I guess I agreed to try to say a few words to get everybody on the same page about what we're talking about. So here we go. So what do we mean by a symmetry of a quantum many-body system? I think a sort of old-fashioned point of view on what's a symmetry is a collection of operators with the following properties. They should commute with the Hamiltonian. Let's see. They should be supported on a whole constant time slice on the whole all of space. They should form a group, and they should be unitary. And so I guess a lot of the progress in recent years on the subject has been reconsidering which of these demands on this collection of operators is necessary. And I think the consensus seems to be that only the first one is really essential. A line of thought that I guess the line of thought that led to this realization starts by noticing that in relativistic systems, Nether's theorem tells us that associates to any continuous symmetry a collection of topological defect operators. So I guess we've heard a bit about them already, but so here I mean a collection of operators associated with codimension 1 surfaces in space-time, not just in space, where the conservation law of the current implies that expectation values with these operators inserted are topological in the sense that you get the same answer if you deform the surface sigma without moving through charged operators or without changing the topological class of sigma. And the fact that Nether's theorem starts with some transformation law, the fact that those transformation laws form a group implies that these operators satisfy a group-like fusion rule up to phases. I guess maybe, if the concept of topological defect operator might be, to people who are used to thinking about systems described by a Hilbert space and a Hamiltonian, might be a little unfamiliar. So let me give a very elementary example of such a thing. In the Ising model, in Euclidean spacetime in any dimension. So there's an operator which we can call U sub -1. -1 is the group element associated to some codimension 1 locus in spacetime, sigma, which is an instruction to change the weights in the partition function, in particular to change the sign of J, the coefficient of the Ising interaction, across any link that's crossed by the surface sigma. So here's some 2D lattice. Here's the surface sigma. All of these bonds are crossed by sigma, and so inserting this operator U sub U-1 sigma in the partition function means what it means is we flip the sign of J on all of these links, and this operator is topological in the Ising model, meaning if I consider U sub U of sigma prime, where sigma prime is some other surface that differs from sigma by some region R, then one can be turned into the other simply by redefining the spins. The spins, after all, are just dummy variables in the partition function. Redefining the sign of the spins that is doing the symmetry transformation, all the ones in the region R. And from that, you can also see that the spin at site X is charged under this symmetry. So that is, if you move this, if you're computing expectation value involving an insertion of sigma X, and you move this operator through that point X, you get a sign. Okay, so defect operators are not really anything mysterious, but it's been realized that reversing the perspective here is very useful. So here we started with Nether's theorem and ended up with the defect operators. So in that sense, they're a sufficient condition for symmetry. So let's think of them as a sufficient condition for symmetry. And this is a nice thing because it allows us to treat continuous symmetries and discrete symmetries on equal footing, because after all, discrete symmetries don't come with currents, but they do come with symmetry operators. And it allows us to treat symmetries that come from Nether's theorem and symmetries associated with like winding numbers and topological quantities on equal footing. And most importantly, it allows various generalizations. And to describe those generalizations, I didn't find a better way than to use this table that I got from Shuheng, which describes various properties of the symmetry operator in that list that I wrote on the first slide, and various kinds of generalizations and which of these properties they violate. Okay, so the first thing we can do is, so an ordinary symmetry is codimension one, the operator is codimension one in spacetime, and at least in a theory described by a topological field theory at low energies, the symmetry operators are completely topological. Meaning you can deform them however you want in spacetime, and you get the same answer, and they satisfy a group law. So the simplest generalization is higher form symmetry, where we just change the codimension in spacetime of the operators. And okay, I guess maybe I'm taking it for granted that everybody agrees that more symmetries is a good thing. But maybe it's worth saying that one reason that we care about that is that, of course, symmetries constrain dynamics, and symmetries can have Tufte anomalies, which constrain dynamics even more. And so more symmetries means we can learn more. Another application is to understand various phases of matter in terms of symmetry. So in particular, discrete higher form symmetries. One application that I think is important is to understand topological order, at least abelian topological order, as spontaneous breaking of a symmetry. Okay, so that's all I'm going to say about higher form symmetry. The next possible generalization is intrinsically non-relativistic, which is subsystem symmetry. So we consider defect operators that are still codimension more than one in space-time, but are not completely topological. So I made one slide about this. Yeah, so we can think about operators that commute with the Hamiltonian. We're not giving that up, but which indeed are not topological in the sense that the symmetry operator acting here has different correlations than the symmetry operator acting here, despite the fact that you can deform sigma 1 to sigma 2. So this has lots of applications. In particular, we can understand gapped fracton phases as phases that spontaneously break so a symmetry like this. And they're related to various other generalizations, such as multiple symmetries, where the current conservation law is modified somehow. And I guess so. Here I was still thinking about an operator that's supported on a manifold, on a submanifold, but we could think about more drastic generalizations where the operator is supported on some crazy other thing, such as a fractal. So here's an example I like is the Newman-Moore model, which is defined by a sum of spins on the sides of the triangular lattice, and the Hamiltonian is a sum of products of z's on the up triangles. So just the gray triangles here. And this has a symmetry, which is I flip all the spins on any pattern of sites which has the property that an even number of sites are incident on any up triangle. So here's an example of a pattern with that property. If you check, every up triangle has either 2 or 0 red dots. And so some consequences of this have been studied by these people. All right, so back to the table. The final generalization is, well, I guess I'm going to say 2 more generalizations. The final generalization on the table is we could give up on the group law. So if the symmetry transformation doesn't arise from if the symmetry doesn't arise from some transformation of say the configuration space or let's say configuration space, then why should it satisfy a group law? In particular, we could allow symmetry transformations that have a kernel that are non-invertible. And so such things are called various things, non-invertible symmetries, categorical symmetries. And yeah, so we just give up on the group law. Instead, suppose that these operators satisfy an algebra. So multiplying 2 of them gives some linear combination of other ones. And this also allows us to describe junctions in between these things. And so this is not a group. In a group, you multiply 2 things, you get a third one, a unique third one. And moreover, if we still demand that one of them is the identity and associate to each label an anti-label, which is just the dagger associated with the dagger of the operator, then in any case where A and its antiparticle fuse to more than one thing, then the operator can't be unitary. Okay, so this is it evades Wigner's theorem. And so one application of this is understanding non-abelian topological order as spontaneous symmetry breaking. It has various other applications that maybe I'll skip. In particular, such things can be anomalous and constrain RG flow. And I think it's so maybe somebody might disagree that we should call this a symmetry, since it's not associated with a symmetry transformation. But I think there's a pretty good argument that it should be. They commute with the Hamiltonian, and perhaps more, and they can sometimes be gauged. If they can't be gauged, there's some obstruction to gauging. That's an 't Hooft anomaly, which is a useful RG invariant, and including them, I think, does a nice job of consolidating various conjectures about the absence of symmetry in quantum gravity. Okay, so maybe a little more advertising of Schuhenning's work. If you ask where can you find them, there seem to be two general answers. One of them is to consider a theory that's self-dual, meaning if you gauge some discrete symmetry, you get back the theory again, and then gauge the discrete symmetry only in part of spacetime. And then the interface between those two things is a duality wall, which is generally non-invertible, essentially because the duality forgets the information about the symmetry action. And so you can't recover the information about where you are on the orbit of the symmetry. And another way to get them is simply to gauge a symmetry on some finite codimension locus, which Schuhenning calls higher gauging. And an interesting further generalization that arises in thinking about this is that the fusion coefficients appearing in this product law of the group elements actually aren't really numbers. They're numbers which depend on the topology of the surface sigma on which the operators are wrapped, and so that it's essentially a topological field theory. Okay, then one final class of generalizations of the notion of symmetry that I think are that has to be mentioned is a line of thought that's been pursued, I think pretty independently by Zhao and collaborators, and also we heard a little bit about it from Dan Fried in some work that he's been doing with Greg Moore and Konstantin Telemann. And I only know about this from watching his lectures at the Perimeter Institute from a few months ago. But the idea is the following. The idea is, well, the claim is that the most general notion of a symmetry action on a d-dimensional quantum field theory, let's focus on relativistic theories for definiteness. So this Q is not necessarily a topological field theory. It can be gapless. It could be anything. But the claim is that a symmetry action on such a field theory is itself a topological field theory in one higher dimension. And it's a particular kind of topological field theory. We make two demands on it. One is that it admits a gap boundary, and the other is that it admits another boundary which has the field theory Q on it. And so these constraints mean that we can make this kind of sandwich where the topological field theory, it's, you can essentially dimensionally reduce it and maybe forget about it, but it's useful to think of it as having some finite extent in the extra dimension. And one end is bounded by the gap boundary, and the other end is this field theory that on which we're trying to describe a symmetry action. And the claim is that the defect operator, the topological defect operators in the bulk of this topological field theory act on Q as a symmetry. And in particular, if you want simply some action of some finite group, some discrete group G, let's say finite group G on Q, then consider the topological field theory to be just the quantum double bond, just G gauge theory in this bulk. And so that's what these guys have been studying. I think at the moment, it seems to be a pretty open question to understand anything about continuous symmetries in this language. But this is obviously a very broad framework for thinking about symmetries, which includes non-invertible symmetries, right? Because if we take the topological field theory to be something other than just discrete gauge theory, well, okay, clearly there are vast generalizations. Okay, so the last thing I want to say is I think in thinking about generalizing symmetries, a question that I found really fruitful is to ask whether enlarging the Landau paradigm, meaning including in our understanding all notions of symmetries and all of their anomalies, whether this is enough to understand all phases of matter and all transitions between them as consequences of symmetry. And I don't know the answer to this question yet. Here's a list which I won't go through in detail of apparent exceptions, most of which have been incorporated by the generalizations of symmetries that I just described. Okay, thanks for listening.
Thank you, John, for a nice introduction of this topic. Next, we'll have Meng giving us a brief summary of exact generalized symmetries on the lattice before taking questions.
Let me just spend a minute connect my iPad to the Zoom meeting. Oops. Wait, what happens? Okay. Oh, you need to allow my iPad to share.
Oh, okay. Maybe Yo can do that. Yo, can you make Meng the co-host?
Yes, it's done.
Oh, yeah. Thank you.
Yeah. Would it be possible to tilt the camera of the computer that's in front so that we can see the audience approximately?
This one.
I'll try.
Okay.
Oh.
Oh, yeah.
Thank you.
Okay, so I'll be very brief. So I just want to give some examples of exact symmetries, exact generalized symmetries on lattice, and I'll focus on those that we probably don't think of them usually in lattice, in the context of lattice models. What I mean is that these, especially these non-invertible symmetries, which are typically discussed in the context of field theories as certain emergent symmetries of a field theory. And I want to just give a few examples where these things are discussed in lattice, partly because I love lattice models and think it gives us a playground to play with and to learn about these generalized symmetries. And also it's good to put things in lattice models sometimes where we have no subtleties associated with field theories. Okay, so first example is a lattice model for non-invertible symmetry 1+1D. This is probably the most familiar, and it's commonly known as Anyon chain in literature. So the setup is very simple to describe. Sorry, what happened? So let's say we have a one-dimensional chain drawn here. So this is a one-dimensional chain, and each edge has some labels on it, and these labels take value from some fusion category. Okay? And we impose the fusion constraints on each of these vertices. So essentially, we think of this one-dimensional chain as a fusion tree of some Anyon theory, of some fusion category. It doesn't have to be a real Anyon theory. And this is our Anyon chain. So in literature, what you often see is that these dangling legs have a fixed label, and just to make it simpler, but we can actually have all of these legs have arbitrary labels from the fusion category as long as the fusion rules are imposed at the vertices, at the sites. Okay. And we can think of it as a boundary of a string net model, or it naturally comes with a non-invertible symmetry because we can first make it into a ring, let's say like this. And to define a non-invertible symmetry, we simply fuse a line of certain Anyon onto the chain. Okay? And we can figure out how this fusion works and what it does to the Hilbert space by basically using the diagrammatic rules of the fusion category. So that defines naturally a non-invertible symmetry in this 1+1D model. So that's one example where we can have exact non-invertible symmetry in the lattice, although the price we pay here is that we have a constrained Hilbert space because we start from Anyon chain. So it's not a tensor product Hilbert space, but it has various constraints, local constraints that we use to define the Hilbert space. So that's also oftentimes a kind of a tension between non-invertible symmetry with the tensor product Hilbert space and even including higher form symmetries that we don't really naturally have them if we have a tensor product Hilbert space. But if we relax the condition, then we can have exact symmetries on lattice. Okay, so a second example of that, still in the context of 1+1D system, is that we can actually formulate at least a large class of them in terms of matrix product operators. So this is a huge class of operators. We don't have to think of them symmetry, just operators that are described as matrix product operators using a tensor network representation. And in this paper back in a few years back, essentially they defined an algebra of matrix product operators satisfying some conditions, finiteness conditions, to make it a fusion category. But we can get a whole fusion category structure once we, if you study the matrix product operator algebra carefully enough. All the details of the fusion category, most of them come out naturally from the algebra of matrix product operators. And different from the Anyon chain, in this case, the matrix product operators they could act on the tensor product Hilbert space, but these operators themselves are more complicated. So that's another example. Now I want to move to 2 dimensions. So first, I'm sure many of us know string net models. And of course, we use them as a model for topological faces in 2 dimensions. But we can also think of them as a model where we can naturally define some sort of non-invertible, quote, one-form symmetries. Basically, we take the string net Hilbert space. In a string net model, we have a trivalent lattice. In the standard string net model, we have a trivalent lattice. And again, we put labels from some fusion category on the edges of this lattice and impose a fusion rule at each vertex of the lattice. Then in this classic paper of Levin and Wen, they worked out string operators in the string net model. Now we can forget about the Hamiltonian of string net model. We just take the string operators as symmetries on this lattice, and they will form one-form symmetries, in quote, non-invertible one-form symmetries. Right now, they are not topological operators because we're not imposing this Hamiltonian constraint on Hilbert space. So that's why I put a quote, but they still resemble close enough the non-invertible one-form symmetries. And if we think along this line, then actually many other examples, well, maybe I'm not sure many other examples, but some other examples are already pretty well known in condensed matter literature. For example, the famous Kitaev's honeycomb lattice model is a lattice model with, quote, one-form like symmetries, okay, exactly on lattice. And there are generalizations of these models. And these symmetries are also quite abundant in the context of quantum error correction codes, because many quantum error correction codes, especially those that are called topological subsystem codes, have this exact, quote, one-form like symmetries, not topological, but still similar enough symmetries exactly in the models. And they play important roles as basically giving you the space to encode quantum information. So for this, there's an expert in audience, Tyler, who probably knows much better than I do. And if there are questions about this, I'll defer to Tyler. We can defer to Tyler for this. Now, there's no, so far as I know, we don't really know any general series of tensor network operators in higher dimensions. In 1 dimension has been studied, formulated pretty well, but in higher dimensions, as far as I know, there's no such series exist. Okay? So we can ask one question that I'm very interested in is whether tensor network operators give us the most general symmetries, at least when we think about non-invertible symmetries and that kind of thing on lattice. Okay? And why we need to use tensor network operators, but not some arbitrary operators on the Hilbert space. That must have something to do with locality. We still want to keep notion of locality in some way, and tensor network operators seem to be a natural way to do that. But it'll be interesting to understand exactly why and what structures we can get from the tensor network operators. Okay, so the last thing, I'll just speculate a little bit about, since we're talking about these symmetries on lattice, we can ask the questions of how symmetry on the lattice interplays with the symmetry in the IR in the continuum. Sort of generalizing what the kind of question that I discussed in talk this morning. And presumably, we would have some mathematical structure that describe the symmetries on lattice, and we will have some mathematical structure that describes symmetries in the continuum, and we would like some sort of map between them. And these things probably would have to be formulated in terms of some higher categories. So I put all of these words in quotes. I don't really know what they mean, but I think I can get away in this discussion without really defining them. And they will also give us, anomaly matching and all these things. So once we start thinking about things on lattice, and this is a natural question that one can ask. Okay, so I think that's all I want to say. Just want to give some examples and may inspire some questions. Thank you.
Thank you, Meng. I guess I will make use of my power as a chair to ask the first question. I have a question for John and probably also Bowen. So in your talk earlier today, John, you mentioned near the beginning, you mentioned two criteria, I think A0 and A1 for the system to have error law entanglement. Do you think that can be generalized to study systems with entanglement entropy that is linear in system size that happens sometimes in fractal systems?
So you're thinking of 3D systems with a subleading linear term?
If I remember correctly, your construction should work for arbitrary dimension. Is that right? So I'm thinking in 3D. In addition to error law, can you also construct some criteria to see whether a system have also linear in L terms?
I see. The answer is I don't know. So certainly the axioms that of the entanglement bootstrap rule out such a term. But it's an interesting question to ask whether, there's some other criteria that pick out ground states of fracton models in the same way that A0 and A1 pick out ground states of liquid models.
Yes.
Yeah, I don't know. That's an interesting question.
Okay, thanks.
Maybe Bowen has something to say. I don't know.
Not really.
Okay, I think my understanding is basically consistent with John's observation. One more thing I can say, but not much more, is that for fracton, if it's a stabilizer model, I think it's still true that the analog of axiom A0 holds, but so then it implies some error law, but it doesn't directly say what's the subleading term, so the linear piece is still missing. Yeah.
Do we have questions from the Zoom audience? Oh, there's a question from Xiaogang. Go ahead.
Yeah, thank you, John and Chengmeng, and it's a really excellent summary. And maybe I just make two comments. One is that for this non-invertible symmetry, I think this Wilson line operator probably is maybe the simplest example. This some kind of a higher form non-invertible symmetry, especially for non-abelian theory. And yeah, that's one thing. But in some sense, the like in one dimension, when you have a symmetry group G, then the Wilson line operator is like a symmetry in the dual model, some kind of dual symmetry. So that's maybe one example. And another comment is that Meng Cheng and mentioned about this how to kind of classify this phase with a symmetry or with a generalized symmetry along this direction. And we feel that this holograph picture maybe can give rise to kind of unified way to carry out this kind of classification, in a sense any phase of matter with certain, at least a finite symmetry, can be viewed as a boundary of some kind of topological order in one higher dimension. So if understanding the bulk boundary relation, then that's maybe a systematic way to understand all kind of phase of matter with a certain symmetry, including symmetry breaking state, topological state, and other things. So maybe in this sense, maybe it's this holographic picture may be helpful. Yeah.
I can ask a follow-up question for Xiaogang. How do you envision the holographic setup answer the question of classifying phase of matter, like with generalized global symmetries at a lattice scale, and want to classify phases with that symmetry? You want to view the whole system as a boundary of a higher dimensional TQFT?
Yes. I think in last you mentioned about this UV symmetry and the IR symmetry, and in a sense, one can apply this holograph picture in both cases. So when you have a system with a UV symmetry, and you can view this lattice system as a boundary of another lattice system in one higher dimension, then the boundary of this higher dimensional lattice model may reproduce all this the allowed phase by this UV symmetry. But then when you think about the IR symmetry, then that means you may have emergent symmetry, and then that means to have to understand those low energy effective field theory with emergent symmetry, then you have to modify the bulk topological order. You have to make a bigger topological order because you have a bigger symmetry. So this IR low energy effective field theory probably can be viewed as a boundary of some topological order with bigger topological orders of the bigger symmetry. And so that's kind of this holograph picture, which is actually very similar to this ADF CFT picture. The symmetry became gauge theory in higher dimension. But here is just a more general, any symmetry became topological phase in one higher dimension. So not just like a group-like symmetry, so any other symmetry.
So are you suggesting that the topological order, the higher dimensional, the one-dimensional higher topological order that we get from the UV symmetry and the one that we get from the IR symmetry, there's some definite relations between them?
Yeah, that's really I don't know, but indeed, you talk about from symmetry point of view, there's a homomorphism, from IR
zero form for group.
IR symmetry. And this homomorphism should generalize to this higher version. And yeah, that's become really excellent question. I don't know. So certainly for the given UV symmetry, you can only have a certain IR symmetry to emerge. And but from a holographic picture, it means given a smaller bulk topological order, it's a IR symmetry can only be certain kind of a larger topological order. But at this level, I don't know how to formulate. Yeah, that's really become an excellent question.
Would that be something like Morita equivalence?
Yeah, there's along this line. And so basically, all this kind of emergent symmetry should also have this holographic picture, accompanying a holographic picture with it. Yeah. Yeah, this really became, indeed, I'm kind of, I don't know what the kind of mathematics, but yeah, I had to learn a lot of new things.
Do we have more questions from the in-person audience? If not, we'll take another question from the Zoom. Oh, sorry.
Maybe not these.
I have a question for Meng. So yeah, maybe it's a basic question. So you described the anionic chain. So there is a chain with some constraint on the fusion that come from some category. So my question is, okay, so yeah, maybe where to look for such system. So for example, if we have tensor product Hilbert space, then then those fusion rules, sometimes those more exotic fusion space can emerge like anyons in a 2D topological order. And so one way I can think of it to treat the, so we first have some larger system for anyons to emerge, then the chain is a kind of a subsystem of the total system. Or are there other ways to find those systems? And I understand that sometimes it's possible to relax further, so the fusion rule may come from a category which does not describe anyons, right? So in general, what are the good places to look for such systems?
So yeah, indeed, I think the original motivation to study these Anyon chains is to use it as a model of anyons in 2+1D systems, Anyon in 2+1 topological faces. You can imagine there's a chain of anyons and there's some dynamics between them. And the Anyon chains was introduced by people in Microsoft Station Q to study such a system. That's the most natural place, I guess, to look for Anyon chains. I'm not sure where we can find these things in other places. For example, experimentally, there has been a lot of discussions about the Fibonacci chain realized in Rydberg atom systems, the PXP models, right, as a low-energy space of Rydberg atom chains, where, of course, the focus there is not on generalized symmetries or low-energy dynamics, rather on quantum dynamics. But you can imagine Anyon chains, because essentially what we have is a tensor product Hilbert space with a local constraint. And local constraint can always be imposed energetically. So it's not crazy to imagine there are certain systems where you realize the Anyon chain as a low-energy Hilbert space. I think what's more demanding is to realize this, to naturally have a generalized symmetries. But that's on top of the local constraint. Local constraint can just impose energetic penalty, and you get it as a low-energy subspace. But then oftentimes there's no natural reason to have a generalized symmetries. So here I introduce them just as a toy model where we can study these things even at the lattice scales. But whether they can naturally arise in some setup, that's not clear. The system with generalized symmetries.
Okay, next Nati has a question. Go ahead.
Yeah, I have some comments and questions. First, I want to thank the people who made the two presentations. I enjoyed them tremendously. But there's something that I think is important that was also mentioned by Xiaogan earlier, and that is the distinction between the UV symmetries and the IR symmetry. This is again something that Meng mentioned. This is very central, and there's a lot of discussion of that, whether there's an emergent symmetry or not. It also came up during Pranay's talk yesterday. There was a question of robustness, and so what we impose in the UV and in the IR, and somehow this was not so central in the discussion of the two presentations today. The two presentations came with some God-given symmetries and then understand the consequences of them without saying are they emergent or not. But the reason I think this is important is that there's been a lot of work about that in the context of ordinary symmetries, when we get emergent symmetries and so forth. But emergent symmetries in the context of higher forms and also the non-invertible symmetries is much more interesting, because when you have a zero form symmetry, which is an emergent symmetry, it's not there at short distances, they're typically irrelevant operators in the IR that violate the symmetry. So if you're not in the absolute deep IR, but you go a little bit higher up in energy, you can see that the symmetry is approximate. An example that I like is that there could be proton decay in the real world, even though it is preserved in the standard model, up to exponentially small effects. That's not the case with high form symmetries. High form symmetries, once you got them as approximate symmetries, they are actually exact. Because in order to violate a higher form symmetry, there's no irrelevant operator that violates it. And this goes back to ideas of Olga Nielsen in the 70s, I think, where he wanted gate symmetry to be emergent, because once you get it approximately there, it is exactly there. And that's something that I think is trying to tell us something, especially because both in the context of condensed matter physics, where there are very few symmetries at short distances, and in the context of gravity, where there is probably no global symmetry at all at short distances, we do see some symmetries in the real world. So the question of how we can get emergent symmetries is very important. And it's particularly exciting for these generalized symmetries, where once you got them approximately, you actually get them exactly.
Okay, do we have more comments or questions? Yeah.
The first comment is that some non-invertible symmetry can also be violated by local operators. So for those, it's not unlike the ordinary symmetry. But following up on that, I actually have a question for Meng. So for ordinary symmetry, there's a homomorphism from GUV to GIR. For non-invertible symmetry, what does it mean to have a homomorphism from one category to another?
Yeah, I guess the short answer is I don't know. I can guess. Yeah, so there's one place where we know the answer, right? So there's one example that's been completely worked out is a classification of symmetry enriched phase in 2+1D, where at least when we restrict ourselves to invertible symmetries, but including the higher form ones, and then in that case, there's still a sort of higher categorical structure, but it's only a higher group, which is much simpler. And there's I guess you can just put higher in front of any word and get the answer and leave mathematicians to figure out what that answer really means. But in the context of 2+1D symmetry enriched phase, we do know exactly what all of these things mean. It's really just mean that you have group zero form symmetry. No, on Lattice, you really just have zero form symmetry and nothing else. But then they can have various junctions and higher codimension defects, and then they'll be mapped into the higher group that you get from the TQFT at low energy, and the relate at each level of higher codimension defects, and there are various consistent relations between them. So if you look up the math literature, the answer is one sentence. There's a higher tensor functors between the two higher groups, and if you unpack that, you get a detailed description of the SCT phase, classification SCT phase. So I imagine once we know the mathematics of the higher structures that emerge in for these symmetries and everything, and then naturally we'll have to define what we mean by maps of functors between these higher structures, and that will describe exactly what that means. Also, obviously I don't know the answer, even in the case of fusion category. Yeah, so sure.
Okay, do we have more questions from the Zoom audience?
Actually, I have a question. Shuhan, could you elaborate on that example of non-invertible symmetry that's violated by local operators?
I guess all I meant is that certain non-invertible symmetries can act on local operators non-trivially. But in 1+1D, that's almost always the case. For example, the energy operator in the Ising conformal field theory is acted non-trivially by the duality line.
Oh, because there's still codimension 1.
That's right.
Mm-hmm.
And yeah, so in general dimensions, for any codimension 1 non-invertible defect, it generally acts non-trivially on local operator. Of course, there are other examples that they don't, such as the condensation defect from higher gauging.
Right, I see. I think, yeah, for Nadi's comment, I think it's important that the operators are codimension bigger than one, right?
I understand, but
That's what I had in mind.
yeah, I understand. But at some point, I think it was mentioned. Yeah. But at some point, Nadi said generalized global symmetries in general. So I just want to say that for some of them, the usual phenomenon still happens.
Great, I understand.
Yeah. Yes. Okay.
Xiaogang has another question.
Yeah, my question is for John. You mentioned this in this holograph picture, the TQFT in one higher dimension required to have a gapped boundary, and whether that condition can be removed. And so one example I can think about is like you may have some kind of a mutual chain summon theory in one higher dimension. Which like anomalous U1 symmetry, yeah. And then that's sometimes this anomalous U1 symmetry require boundary to be gapless, and whether this that's whether whether this can be a case where you don't even have a gap boundary. Yeah, there's some issue here. Yeah, what is do we have any qualifier to topology order in one higher dimension so that they can describe the symmetry, or any topology order? I'm really bothered that's whether should I even include invertible topology order? The invertible is the furthest from symmetry. Yeah, I don't know. I'm kind of puzzled by this. I wonder whether you have some thought.
Well, the reason I added that condition is I kind of understood this picture of the sandwich, right? I like that picture because it means that the higher dimensional topological order is really, you could think of the sandwich as very thin, right? It's really not like an extensive system extending off forever. So I found that made me more comfortable with the idea. I think in Dan Fried's presentation, he required this. But I agree, it's very interesting to ask whether it's really necessary. But I don't. So do you see a way to? So I guess if you.
My understanding is the following: when you have the other gapped boundary, my understanding of other gapped boundary is like a UV regulation. That is suppose you have a quantum field theory which can reveal the boundary of TQFT, but TQFT can have another gapped boundary, and then you can view a different choice of a gapped boundary as a different UV regulation of same quantum field theory. That's one way to understand it. But however, if a bulk topology order don't have a gap boundary, that means you truly have a trouble to UV regulate the quantum field theory. Then maybe this quantum field theory is really can only be viewed as a boundary for bulk. There's no other choice. But however, from I don't know, from purely low energy effective quantum field theory point of view, if you say we don't need to know UV regulation, whether that means we can remove this gap boundary condition. Yeah, that's maybe a little bit along this direction.
Yeah, I don't know. I like the ambition.
Yeah.
Okay, do we have more questions from the audience?
Hi, I have a very naive question, which can maybe be summarized as why stop at fusion categories? John's definition of symmetries just said any conserved quantity of the Hamiltonian could be considered as a symmetry. Arguably, you'd want to have some additional structure for it to be useful, but why stop at fusion categories?
Well, I guess what I had in mind is you want to be able to multiply them, right? So if you want to be able to insert not just one of them in the path integral, but multiple of them. And I guess if it's isn't it sort of automatic that you get a third one from the product, right? Since
yeah, with the Hamiltonian.
So okay, I guess so when you know, all right. The word fusion category comes with a lot of other baggage, and I think that stuff is necessary, because in addition to just putting them on top of each other, you also can consider various other like networks of the symmetry operators, right? Like trivalent junctions of them and things like that. And then you can also think about like 4-valent junctions and try to resolve those as 3-valent junctions, right? And I think in order for the whole story to be well defined, you need to say how to do that, right? How to write the the 4-valent thing in terms of as a sum of in terms of 3-valent things, and that's where the F symbols come from, right? So I don't know, but I suspect that in any realization of this structure where you have some operators which are not invertible but commute with the Hamiltonian, I think that information will still be specified, and so I think you'll end up with a fusion category. I don't know. Maybe somebody else has something more intelligent to say.
Moon, do you want to add anything? Okay.
I don't think it's necessarily a fusion category. Well, I'm not an expert in the category world, but I think generally it can be something more general than just a fusion category, right? It could be a fusion N category, or it could be something like in higher space-time dimensions. I don't think it's a fusion category. There's the notion of F symbols or associators are not exactly the same as those in 1+1D. Yeah. So I don't think we stop at fusion category. I think that's the short answer.
Are there more questions from the Zoom audience? Did Nati have? Yeah, go ahead, Nati.
Yeah, so this was prompted by the comment about the sandwich and Shaugan's picture of the UV. My understanding of that is old-fashioned because I've been decoupled recently. But the sandwich, when I understood it, was a device to change some global properties of the theory. For example, SUN versus PSUN. You do that with a sandwich. That's not the same as changing the UV properties of the theory. So I think this is a kind of totally unrelated notion. I see some people are nodding, and I hope this is with agreement.
Okay, we have one more question from the in-person audience.
Yeah, maybe this is like an example-driven version of Tyler's question. So if you take something like a commuting projector Hamiltonian, like what would you say about all of the Hamiltonian terms in terms of symmetries of the Hamiltonian in this language?
The question again. So is a question that if I'm a commuting projector Hamiltonian, what can we say about the Hamiltonian parameters from the symmetries?
Like each term in the Hamiltonian is not very
Right. Yeah.
Generalized symmetry. What would you say?
I guess I can. I was just thinking about the example where this really means something. The string net example where the Hamiltonian terms is literally the smallest loop where we define the one-form symmetry, the non-invertible whatever one-form symmetry, and by imposing the ground state condition, we basically say that the symmetries are topological. So in that case, we can interpret the Hamiltonian, the terms, basically as saying like, these symmetries are satisfied. And these symmetries are topological, and we have the TQFT. But in general, I guess probably many TQFTs, many community project Hamiltonians can be interpreted this way. Like these terms are basically the smallest smallest symmetry operators you can write down for certain invertible or non-invertible higher form symmetries, and we just impose that to create a Hamiltonian.
Do I have more questions from Zoom? Then more questions from the in-person audience?
So during Meng's talk or during the more general panel discussion, there has been a lot. So there are some discussions about the tensor factorized Hilbert space. So I guess my general question is, why do we prefer a tensor factorized Hilbert space? Is it just for simplicity or not? I have this question because I was raised as a quantum field theorist, and in quantum field theory, the Hilbert space never tensor factorized. So I'm just curious from the lattice point of view, is it people like it just because it's simple, or is there something more conceptually non-trivial?
I think that one way in which it's important is, at least my understanding of the equivalence relation on phases of matter involves not only deforming the parameters of the Hamiltonian, preserving the gap, but also adding and removing decoupled degrees of freedom. So yeah, stacking on top some dust of disentangled qubits and then entangling them by adding interactions is part of the equivalence relation. And so, the trivial phase is the one represented by a product state, right? So I think that's the point of view from which I find, product states comforting. I don't know.
Maybe I can add a comment. So my feeling is that the tensor product Hilbert space, of course, it's the one that we study all the time in solid state physics, so we naturally think about those. But a tensor product Hilbert space versus a tensor product Hilbert space with local constraints, I don't think they are really that different in terms of global structures. Of course, no, they look very different, but I think they are still somehow should be thought of in the same family of models. What's really different is a tensor product Hilbert space, or those with local constraints. But then on top of that, we also add global constraints, which will change fundamentally many of the things that we talk about, like anomaly or things like this. Yeah, I think that's probably where the real difference comes in. But before that, as you said, in quantum field theory, you never have a tensor product factorization to begin with. But there's still some structure that imposes on the operator algebra. At least sometimes or as far as I know, it's often imposed also implicitly. Things like, again, I'm talking about things that I don't really know very well, like Higgs duality on the operator algebra, which is, I believe, is basically a proxy for tensor product factorization at some form. But okay, I could be completely wrong there. So
I'd like to grab the microphone without permission, because I don't fully understand. Shuheng must have something deeper in mind, because my understanding of all the systems in continuum field theory is that deep inside, we can think of them as associated with some Hilbert space that factorizes locally, perhaps with local constraints, and perhaps with global constraints. Now, the local constraints are clearly not that harmful. Even the global constraints, in most cases, we know how to describe them as gauge fields. So in that sense, I think we're talking about the same beast. We describe them differently, but we describe the beast differently, but it's the same beast. So I don't think this restriction is that big. And I apologize for grabbing the microphone.
The thing I have in mind on the field theory is the rich slider.
I can't hear you.
The thing I have in mind when I ask the question is the rich slider theorem in quantum field theory.
Following my former president, I will take the fifth here.
Then a comment or question from Xiaogang.
Maybe there's another angle to look at this. It's about this landscape. If you start with a tensor factorized Hilbert space, some lattice model, then there's a landscape of a low energy effective quantum field theory. And just then it's just a question that whether the so-called good quantum field theory all belong to this landscape or not belong to this landscape. And but we know that there are so-called anomalous quantum field theory do not belong to landscape, belong to swampland. But on the other hand, they can be viewed as a boundary of a tensor factorized theory in one higher dimension. But sometimes I kind of wonder, do we have some kind of a quantum field theory which have even worse, which cannot be even viewed as a boundary of a tensor factorized lattice model in one higher dimension? I don't know, but actually I think one theory may come into mind is this single, I forgot, it's a 3+1 dimensional single wild fermion with SU2 weight anomaly. I wonder whether that can be an example, maybe even worse. It's not.
But doesn't that arise at the edge of a theory, a 5D theory with a direct
with dynamical gauge field? I mean, the gauge field is truly dynamical, not background SU2. There's a 2 SU2 anomaly, the old one, the new one. New one is as a boundary for W2, W3, but the older one, I think maybe in some sense have a worse anomaly. In that case, there's a global SU2 transformation, gauge transformation changes sign of a partition function. I don't know, yeah, whether that's be. If that make if SU2 gauge field is dynamical, that's kind of worse. Yeah, I don't know, but this, I wonder whether this relates to Shihong's question, whether there are quantum field theory which not associated with a tensor factorized state at all. I don't know. Yeah. But in some sense, this landscape picture, I don't know. It's this landscape is really raised as a field theory which is compatible with quantum gravity. But when you're looking at those kind of conditions, it's amazingly similar to landscape of a lattice theory with no symmetry. Yeah, like emergent gauge theory should carry all the representation and things like that. That's very much like this.
Xiaogang, so regarding your question about SU2 weight anomaly, will the same question arise if we have a theory with the anomaly and we just try to gauge some part of the symmetry?
Yes or no. Maybe for continuous symmetry, maybe there could be trouble. For discrete symmetry, I think you can always gauge. You can gauge the symmetry in one higher dimension at least. Then
let's say we try to gauge in the same dimension.
Yeah, same dimension may have trouble. I don't know. Yeah, maybe in the same dimension there may be a trouble. Yeah.
But in that case, oftentimes when you can gauge a non-anomalous subgroup, and you just modify. Sometimes you modify the symmetry, introducing new symmetries, or just change the group structure.
I see.
Yeah.
But I just try to say that so when you have this SU2, you really have dynamical SU2, then as view that as an effective theory, and then whether this theory can emerge from some tensor factorized state or not. There's a yeah, that's the issue.
I think if
Can
you
you
want,
explain what you just said? I didn't understand what the issue is. The theory that is inconsistent, the SU2 coupled to with one doublet, where the SU2 is dynamical, and there's a theory which is consistent, the same one without the SU2 gauge field. And then there is the new anomaly that you wrote about, but that's not an inconsistency of the theory. So
Yeah.
So what's okay? So that I understand. Then what? What's the next step?
I think the question is whether there can be some anomaly inflow that fixes the Witten anomaly, right? Is that
Yeah.
and doesn't that happen if you have if the SU2 gauge field also lives in the bulk? Because then I can just have a.
But the bulk will be gapless. That's a problem.
Yeah.
If I think if SU2 in the bulk can be gapped, and the boundary is gapless, that would fix the problem. But that's we don't know. Yeah.
But why should we always demand that the bulk is gapped?
Because it's a low energy effective theory. Otherwise, the low energy effective theory would have a bulk.
Okay. Yeah, I agree.
I think this is unnecessarily complicated. Let's consider another model, SU3 with 1, 3. So you also have an anomaly, but it's perturbative. You don't need to go to non-perturbative physics.
Yeah.
So could you ask your question there? So I start with 3. It's a global SU3. I try to gauge it, and it has an anomaly.
Yeah. I think that's true.
And for that matter, I can even let me even make it easier. Start with one chiral Anyon and try to gauge the U1.
Yeah, perturbative anomaly may all have this feature. Yeah, I've been thinking about this. Yeah.
Xiaogang, is that a question just for continuous group? Because if you try to look at a theory with anomaly of some finite group, and we can imagine the bulk also has the gauge field also extends to bulk.
Yeah.
Then everything gauged in the bulk and it's gapped, and there's no.
You can gauge the bulk, then
we have a non-invertible bulk.
Yeah, exactly. Yeah.
But
so whether gauging the bulk would that can be viewed as a as a lattice theory in the bulk, which regulates this using anomaly inflow to regulate this boundary theory. Yeah.
It's a somewhat very unconventional inflow because now the bulk also has dynamical degrees of freedom, so the boundary theory is not so well defined.
Yeah.
But does
SU2 can be regulated by the lattice in the bulk? Whether I think the question that when you have perturbative anomaly, maybe you could have you even have a theory which cannot be regulated by the lattice theory in the bulk. That's kind of, I don't know, worse anomaly.
Do we have more comments or questions from the in-person audience? All right, more Zoom audience? All right, if there are no more questions, thank you everyone for your discussions.